Hello, everyone. This is the beginning of lecture number 10, the second and last lecture for chapter 6. So we'll do the second half of chapter 6 and continue on with the discussion that we've been having about the relationship between impulse and change in momentum. We had a couple examples from the earlier lecture, so we'll continue with that today. I want to point out in this particular slide, you see two examples of a truck that is coming to rest or stopping with after it started with some initial velocity, which we will call V. V could be like 20 miles per hour. And it's going to come to rest in entirely different ways. In the first case, the truck hits what we call a haystack, and there's a gradual slowdown of the truck till it reaches its zero velocity. And in the second case, the truck hits a brick wall and it stops abruptly and immediately, or we should say in a very short time. Now, in both of these cases, the change of the momentum of the truck is the same. It started out with some velocity v. It came to rest at some later time t, and it is no longer moving. So the change in velocity is the same in both cases. Therefore, the change in momentum, which is mass times velocity, is the same in both of the cases shown here. The only difference is that the time factor, that it plays a role in how quickly the truck stops. And so because of the fact that the change in momentum, which in this case is simply equal to the initial momentum, since the final momentum is equal to zero, that this change in momentum is given by the product of the force times the time over which the force acts on it. In the case of the haystack, the truck slows down much more slowly, and therefore the time over which the deacceleration of the truck occurs is much longer, and than the case where it hits a brick wall. So since the change in momentum is the same in both cases, and the time during which the momentum changes is much shorter in the case of the hitting the brick wall, then we can conclude that the force of impact is much higher than in the case where the truck hits the haystack. So we see here that that this in fact tells us why we have a much safer scenario with a haystack. We use the same analogy when we have airbags deployed on the steering wheel, so that our head velocity moving forward gets slowed down much more slowly than if it goes to the hard windshield, which will be an abrupt, very short time of impact, and therefore the force of the impact is much stronger. If my head hits the airbag, then the time over which the head is slowing down is going to be much longer, and therefore the force on the head is much less. So it's another example where force times time is the same in both scenarios, but if I can extend the duration of time over which this slowdown occurs, then I have much less force that's being applied to either the vehicle or the human inside the vehicle. Now, in this slide, the same principle is being applied to the impact of a fist upon the face of a boxer. And you can see here that if the boxer leans into the punch, he is going to have much more damage to the face than if he lets his head go backwards with the punch to slowly absorb the impact. And that's because the force on the boxer is entirely different and much larger when he leans forward into the punch rather than let his head go backwards as the punch comes through and comes to a stop. So in this case, we also have the momentum of the head that is going from uh, some initial velocity to some final velocity. And if I ride the punch, so to speak, which is the first picture on the left, then the time duration over which the force of the boxing glove is applied to the face is stretched to a much longer time than if the head is upright or leaning into the punch. And therefore, since the time duration of that impact is much shorter, the force will be much higher because on the right side of the equation, P initial minus P final, that is the same in both scenarios. What differs in the two scenarios is the time duration over which the punch is delivered. So if the punch is delivered over a much shorter time, such as the example on the right, then there will be a much higher force. But if the punch is delivered over a much longer time, as the boxing glove slows down and the head bends backwards, then the force of impact to the boxer will be much less. And again, this is a exercise of the principle that force times time is equal to change of momentum, where the change of the momentum is the same in both these cases, just as it was for the case of the truck hitting the wall or the haystack. Okay, now in this slide, we have an opposite type of scenario compared to the previous slides, where in this case, we have a karate expert that is splitting a stack of bricks by bringing her arm down swiftly with a large momentum. And therefore, because this is done so quickly, the momentum changes abruptly from the high-speed impact to zero when the hand stops going down any further. And we want to make that time of impact to be as short as possible. Now, regardless of how she brings her hand down, the change in momentum is going to be the same. It'll be her initial velocity times the mass of the arm, and then the velocity goes to zero. So that's going to happen regardless of how fast she brings her arm down. But if she wants to deliver the maximum force, she wants to bring her arm down and hit the bricks with as short of time as possible, in which she delivers the full momentum of her hand and arm against the stack of bricks. That way, by shortening the duration of the time, the force of impact will be much higher, and therefore the bricks will break apart as shown in the picture. If she were to do this in a much slower way, then what would happen would be that the force of impact would be much lower, because the duration of time over which she delivers that impact or that force would be extended such a long time that there would be insufficient force to actually break the bricks. So remember that the key to the last several slides is that we're looking at two different scenarios where the force times the time duration is the product of those is the same, because the momentum change is the same regardless of how fast the impact occurs. What does change is the force if I'm able to deliver if I'm able to bring the momentum to zero in a much shorter time. Okay, now in this slide and the next slide, we will examine the effect of objects that bounce off of other objects when they impact when they provide an impact upon them. The example that's given here is if you wanted to catch a falling flower pot and slowly reduce its momentum to zero and then you throw it back up again, then you provide an additional impulse equal and opposite to the impulse that was used to slow down the pot as it was falling. So there's one impulse that slows it down as you catch it coming down, and another impulse that is given as you push up and cause the pot to return in its upward in an upward trajectory. When this occurs, we have twice the change in momentum, and this is simply because the initial momentum is down. It slows down to 0, and then it goes back up to the same positive value. So the change in momentum is double what it would be if I simply caught the pot of flour, the flour pot, and kept it at rest. That fact that we double the impulse occurs whenever an object is bouncing. And as you'll see in the next slide, there's a practical example that if you want to turn a paddle wheel at a maximum with maximum velocity to use for it to do in order for it to do work, then it's more advantageous for the water to bounce off of the paddle wheel and go back up. Now, in this slide, we show the effect of what happens by designing a paddle wheel to cause any falling water onto the paddles to bounce back up off of the paddles and make a U-turn after they have impacted onto the surface of the paddle, which is in this case curved, and therefore causing the water to return with a velocity that is approximately equal to the initial velocity that it had on its downward trajectory. By increasing this momentum change of the water, we deliver a higher impulse to the paddle wheel itself. So, for example, or as shown here, if P sub I is the initial momentum of a drop or a quantity of water onto the paddle, then that drop will bounce back up upon hitting the paddle, and therefore the change in momentum will be twice the initial momentum of the particle. That means that it can impart a greater force onto the paddle itself, therefore causing the wheel to turn faster. And since we want the wheel to turn as fast as possible so that it can do some useful work for us, then that's a beneficial thing to increase the force on the paddle. So that is the idea that we have, where the bouncing effect, by doubling the change in momentum of the water molecules as they hit and bounce back up, then effectively doubles the force of impact on the paddle wheel, causing it to turn faster. And this, of course, is exactly what one would like to have happen. Okay, we're going to conclude this chapter with a discussion of the concept of conservation of momentum, which is a fundamental pillar in the nearly all fields of physics, and it is a principle which we have observed over and over again. And basically what the principle says is that in the interaction between any group of particles, usually we consider one or two particles to be an event that corresponds to a collision or an interaction, that at any given time, the sum of the momentum of all the particles before the interaction is equal to the sum of the momentum of all the particles or objects after the interaction has occurred. So this is a very powerful rule that basically tells us how to calculate many quantities or many properties of the velocity of objects after they collide. We'll have an example later on in the lecture. But for right now, I want to hold your attention to the figure that you see in front of you, where a cannonball has been fired. Now, we know from previous discussions that when the firing of the cannonball occurs, the ball will exit the nozzle of the cannon with a velocity that is can be rather high from the explosion, with the intention, of course, of destroying the enemy or the enemy property. So at the same time, there is a force or what we would call a recoil of the cannon itself as a result of the explosion. So we analyze this from the point of view of conservation of momentum. And basically, in this particular example, what we say is that the momentum of the cannon and the ball before the firing are each equal to zero. So the ball is at rest and the cannon is at rest. If I now fire the cannon so that the ball exits with a high velocity, then in the absence of any friction, we'll say for right now that the cannon is sitting on a sheet of ice instead of on a rugged, rough bed of gravel that you see in front of you, then the cannon will recoil in the opposite direction. So the conservation of momentum says that if the sum of the momentum of the ball and the cannon, they're each equal to zero before the firing, then they are equal, the sum of them is equal to zero before the firing. And so after the firing, in the absence of any external forces such as friction, then I must have the equation that you see, which is, excuse me, the mass of the ball times its velocity plus the mass of the cannon times the velocity must add up to zero, which clearly states that the velocity of the cannon will be opposite to the velocity of the ball, as we know from its property of recoil. So the conservation momentum can be applied here and give us a very accurate picture of what's going on. Now the next two, this slide and the next one, are basically a repeat of what we have already said in the previous slide. So I'll let you read this on your own. There's not really any new information here. We will work a couple examples in slides to follow that use this conservation of momentum principle. But for now, I'll let you read this, and we will resume in a couple slides. Now, billiard balls are the easiest way to look at elastic collisions because they occur largely without friction. We can observe their effects with conservation of energy and momentum occurring, and they are relatively easy to analyze. So there are three separate scenarios in this slide. One in which the cue ball, as I like to call it, on the pool table hits the 8 ball, which in this case is orange actually, and the green ball is the cue ball, hits it at rest. Then when it strikes it, it imparts all of its momentum to the orange ball, and it carries away an equal velocity that the green ball had before it made the impact. So this is a case where we obviously have conservation momentum, the mass times velocity of the green ball, plus mass times velocity of the orange ball, which is when its velocity is zero, is equal to the mass times velocity of the orange ball that you see in the lower right corner of the figure labeled A, which is the third figure in which you can see the ball of the struck ball carrying away the momentum from the green ball. Now, that's clearly conservation momentum because the mass times velocity is simply that of the green ball. The mass, and we will assume for now the mass of the green ball and the mass of the orange ball are in fact the same. They look the same size and more than likely have the same composition. So the mass times velocity of the green ball before collision is equal to mass times velocity of the orange ball after the collision. Since the green ball is at rest after the collision, and that would therefore conserve momentum. Now, another scenario that we can look at is the elastic collision between two billiard balls that are colliding together with equal and opposite velocities. And after they strike each other, they recoil with the opposite velocity that they had for each one. So one can see here that the sum of the momentum of the green ball plus the orange ball, which actually is more like 10, I guess. I probably didn't label that color correctly, but the mass times the velocity of the green ball plus the mass times velocity of the orange ball adds up to 0 because their velocity vectors are in opposite directions. Similarly, therefore, after the collision, they have to add up to 0. So whatever velocity the green ball has, the tan ball must have an opposite velocity to that because the sum of the momentum of the two objects must add up to 0. All right. Now, in the third scenario, which is labeled C in this plot, the green ball strikes the tan ball. The tan ball has some velocity to it already moving in the same direction, but a lower velocity than the green ball. So at the time of impact, what could happen is that the tan ball absorbs velocity or momentum from the green ball. The green ball slows down, the tan ball speeds up, but the sum of the momentum afterwards, as you can see from the length of the vectors, is the same before the collision as after the collision. So this allows us to calculate the velocity of the ball in both scenarios. Now, inelastic collisions can also be shown to conserve momentum, just like elastic collisions, which we studied in the previous slide. Here we consider the case where there is a freight car that is traveling with velocity v equal to 10, we can say 10 meters per second, for example. It strikes a equal mass object, which we call the green car, which is initially at rest. And after the impact, they are linked together by a link at the base of the car. And then they travel off with some new velocity after the impact and the cohesion of the two cars occurs. So in this case, we can apply conservation of momentum to this case. This is called an inelastic collision because the number of objects before the collision is different than the number of objects after the collision, since the green and the red car move away as one object after they collide. So in this case, as we just mentioned, we have a velocity of 10 meters per second. It strikes an equal mass car, and then it travels off with a new velocity. Now, if the mass of the green and the mass of the red are the same, then now the mass of the unified object of the two-car system is twice as heavy, or has twice the mass, and therefore, by conservation momentum, its velocity will be half of what the red car was before the collision. So if they travel off together, we have beforehand that the mass of the red car times 10 is equal to twice the mass of the combined car, twice the mass of the individual cars times the new velocity, and therefore the new velocity is equal to 1/2 the velocity of the red car. That is to say, the velocity of the combined red and green car system acting together. Okay, in this slide and in the two that follow this, we're going to give further examples of inelastic collisions. This one is the case of a green fish, which is moving through the water at 1 meter per second, and it eats an orange fish, which is moving in the opposite direction at 4 meters per second. And the green fish is 5 times heavier than the orange fish. The green is 5 kilograms, and the orange is 1 kilogram. And the problem is that after the green fish eats the orange fish, what will be the new velocity of the green fish after he swallows the orange fish? So this is an example where we can use conservation momentum. We basically take the product of the mass of the green fish times its velocity. So in this case, it's 5 kilograms times 1 meter per second. Gives us the number 5 for the momentum of the green. The momentum of the orange fish is minus 4 uh, kilogram meter per second, which is to say that it's the product of the mass times its velocity in the negative direction. Therefore, we have a minus sign where you see the velocity as minus 4. And that is the total before. And so if I add up those numbers, I get a number which looks like 1 kilogram meters per second. On the other side of the equation, we have the momentum of the green fish after he ate the orange fish. So now in this case, what happens is that the green fish now weighs 6 kilograms instead of 5 because he's just swallowed a 1 kilogram orange fish. And it moves off with a new velocity v. So we can see from this that on the left side of the equation, we have it numerically equal to 1. On the right side, it's equal to 6 times v. So 1 equals 6v means that v is equal to 1/6 meters per second, and that will be the velocity or the new velocity of the fish after he had after he had the lunch. So I'm trying to see if I make sure I got that correct, but yes, it'd be 1/6 of the meters per second after he had his lunch. In this slide, we have another example of an inelastic collision, only this time we imagine that there are two cars that are traveling orthogonal, perpendicular to each other, and they collide at the intersection. And as a result of the collision of the intersection, they then stick together and move off as one object, shown here at roughly a 45-degree angle with respect to uh, to the vertical direction. So what we can do here is to apply the same rule for conservation momentum. As before, we are working the cases where we can neglect friction entirely altogether. So we have to imagine that these cars are moving on a sheet of ice with almost no friction whatsoever. When they collide, they stick together, and then they go off at a 45-degree angle. So this is a particular case where we have to know in advance what the speed or velocity of the two cars are before the collision so that we can calculate what its velocity is after the collision. And furthermore, we have to look at momentum. Since it's a vector, it will have a component of momentum which is in the vertical direction on the slide that you see here, and there'll be component of momentum which is in the horizontal direction, which you also see. So in these more complicated cases, then the objects recoil together. If their velocities were equal before the collision, then after they collide together, one would see them moving off at exactly 45 degrees. And that's exactly, of course, what you see in the figure. This is still inelastic because just like with the trains colliding, they stick together after the collision and move off as one object. And finally, we have the last slide in the chapter and the last slide on inelastic collisions. And this one shows another example of a exploding firecracker which is moving vertically in the downward direction before it explodes. And what we can find, calculate this from this, is that we look at the effect of what will happen after the explosion occurs. And after the explosion, the firecracker breaks apart into a various number of pieces, depending on the type of explosion. The paper from the firecracker will move apart in different directions at the explosion. But vectorially, when we add up the momentum of all of the pieces of paper that result from the destruction of the firecracker, then those momenta of each of all of the particles will add up to the original momentum, and therefore the net result is that the sum of the momentum of the individual fragments of the firecracker will have the same velocity, which is shown as a downward arrow of mass times velocity, as one had before. So momentum is conserved. It may be that some pieces of the firecracker will move opposite direction to the initial velocity of the firecracker. But if I add up all the pieces that are generated of the firecracker after the explosion, they add up to the same momentum, which is m times v, the mass of the firecracker, times its initial velocity before it exploded. And this gives our final example of a conservation of momentum.